Here's a bunch of empty space. If I drop a single positive charge in the middle, what happens? An electric field is created. There's nothing in the surrounding space. It's empty. But we still draw these arrows. What do the arrows represent? I mean, there's nothing here, so why can we draw an arrow? The arrows show the electric field, but specifically they show where would a positive test charge get pushed. We base the electric field on a hypothetical test charge, and we always make that test charge positive. So if you come over and you put your positive test charge at this location right here, it is pushed and repelled because positive and positive repel. If you put your positive test charge over here, it is repelled with a bigger force because it's closer. If we clear this out and put a negative charge in the middle instead, we get a very similar picture. The lines enter along radii. We call this a radial field. So if I put a positive test charge at this empty point in space, it's attracted. Positive and negative attract. If I put a positive test charge much farther away, it's attracted but with a weaker force. The electric field is always based on a positive test charge. If we put one positive here and one negative here, they kind of bend around like we learned. And if we put a positive near another positive, they kind of curve out toward the middle as they approach the middle. But what if I make a whole row of positives and a whole row of negatives? What happens then? If we keep going, the picture looks like this. And we see that in the middle, the arrows point straight across to the right. This is called a uniform electric field. At the top and bottom, there's this curving of the field line. But in the middle, the lines all point to the right. And in fact, those lines represent an electric field that is the same strength everywhere. If you walk up and you put your test charge right here, every newton, every coulomb in the charge is pulled with maybe, let's make up a number, 4 newtons per coulomb in your charge. And if you walk over to here, that charge still feels the same 4 newtons per every coulomb. And if you put it over here, guess what the value is? The number is 4 newtons per each coulomb. So not only does the value or the magnitude stay the same, the arrows all point to the right. The direction is the same too. We create this between 2 plates. So we're not talking about just a 1D picture. You can imagine that the plate kind of stretches out of the page. And here's the other plate. They're facing each other. And on one plate we put a bunch of positive charge. And on the other we put a bunch of negative charge. And we're going to ignore the curving that happens, but in between, in the space between, there's this kind of uniform electric field. The arrows point in the same direction. The strength is the same everywhere. Maybe it's something like 4 newtons per every coulomb in your test charge. It doesn't have to be 4, it could be something different. I'm just making this number up. We don't have to have the positive charge on the left. We could switch the two, and then the field lines would switch. So if you walk over and you put a positive test charge right here, where is it pushed? Positive charges are pushed in the direction of the field lines. It would be attracted to the negative and repelled from the positive. It's pushed to the right. And if you grab that charge, but then you let go, what's going to happen? If the charge feels an unbalanced force to the right, it's going to fall and accelerate to the right. Positive charges fall toward the negative plate. Positive and negative are attracted.